Hello everyone, we're going to be talking about bonding today. So we're going to be talking a little bit about how atoms come together, how they react with one another, and talking about the different types of bonds that can form between them. So we're going to start first off by talking about compounds and molecules. Make sure that you have your version of the PowerPoint open so that you can take notes as we go. So to start, molecules are substances with two or more atoms chemically combined. A compound is a molecule made up of atoms from two or more different elements that reacted chemically and have unique chemical properties of their own. So while all compounds are molecules, not all molecules are compounds. Some are pure elements like H2 or chlorine 2. So what this means is basically that molecules are basically any combinations of atoms, including ones that are, say, two of the same type, while compounds have to include at least two different types of element in order to be a compound, right? So here's just some examples, right? And if you feel like you know these and you want to write them in before I actually say them, you can always pause and do that and see if you're right. But here's a list of different molecules, and we're going to decide whether they're compounds or pure elements. So H2, two hydrogen atoms, would be a pure element. NaCl, that would be sodium chloride, that would be a compound. CO would be a compound. HCl, also a compound. Compound, compound, compound. O2 would be a pure element. Chlorine 2 would be a pure element. This would be a compound, and this would be a compound. So you'd see if you guessed on those, see if you got those right. Alright, so what determines how atoms are actually going to bond? We've talked about this already. It's the number of valence electrons. Those are the electrons in the outermost shell. Alright, so atoms generally need 8 valence electrons in their outer shell to be stable. The only exceptions would be hydrogen and helium, because they only have one shell, and that first shell can only hold 2. They are stable if they have 2 electrons. Alright, so they're the only exception. Everybody else wants 8 valence electrons to be stable or complete. Ions. So ions are atoms with an electric charge. If an atom loses an electron, it becomes a positively charged ion. And if it gains an electron, it becomes a negatively charged ion. So which atoms become ions? Alkali metals have just one valence electron, right? We talked about this in class. It's much easier for them to just dump that one electron so that they don't have an unfinished outer shell. And when they do that, they become positively charged, or +1 charge, because they're just dumping one electron. So they end up with a +1. Alkaline earth metals, since they have 2 valence electrons, they've got to dump 2 of those electrons, and they end up with a +2 for that reason. And then you've got the halogens. They've got 7 valence electrons. They can't really get rid of 7, or it would be a lot of work. So it's much easier for them to gain 1. So when they take on 1 electron, they end up with a -1 charge. Other nonmetals can also gain electrons. Oxygen, for example, needs 2. So that would end up with a -2 charge if it gains those 2 electrons. Alright, so the first type of bonding we're going to talk about is ionic bonding. And ionic bonding is when ions of opposite charges get close to each other, they tend to attract. We talked about this when we talked about magnetism and electricity. Opposites attract. So what happens typically, especially with good old table salt, you end up with a sodium element that has 1 extra electron. And it wants to dump that, so it ends up giving it to chlorine. And chlorine only has 7, it wants that 1 extra. So when that happens, sodium becomes positively charged, a positive ion. Chlorine becomes negatively charged, a negative ion. And they have an attraction to each other for that reason. So after it's generously given its electron up, they're now attracted, positive and negative. And that's how ionic bonds work. It has to start with an electron transfer of some type. One becomes a positive ion, the other becomes a negative. and they form an attraction. They form a compound for that reason. And sodium is a really good example. Sodium chloride is a good example of that, table salt. Very cute. So how do other elements bond? Another type of bond is called a covalent bond. All right, so this is when elements, we call it sharing, and this is typically the non-metal groups. They like to share electrons rather than just transfer them from one to the other. It's not exactly sharing. It's more like a tug-of-war, a fight between them. They each want the electron, and it just kind of ends up sitting in the middle of them. Right? So it's like a fight over electrons that they both want. A good example of this would be a water molecule. Right? Hydrogen has one valence electron. Oxygen needs two valence electrons to complete its outer shell. So if it shares electrons with two hydrogen molecules, H2O, then they all get what they want. They form a covalent bond. There are really two types of covalent bonds, though. There's something called a polar covalent bond, and a good way to remember this is to think of a polar bear, right? And think of polar bears as not being the best of sharers. While they're sharing the electrons, they don't share them equally. So one of the atoms is going to have more of a pull, and it's going to pull those electrons a little bit closer to itself, while the other electron still has it in its grasp, but it's a little bit further away. And what results is that that one electron that it's further away from becomes a little bit positively charged, because the electron's further from it, and the one where the electrons are closer becomes a little bit negatively charged, so there's a little bit of an attraction there. This is kind of like a in between an ionic bond and a covalent bond. There's a polar covalent bond, because there's a little bit of negativity and attraction there. All right, the other type of covalent bond we call a nonpolar covalent bond. So if they're not polar bears, they share equally, right? And the electrons just end up sitting right in the middle. They equal distance, so there's really no difference in charges here. Absolutely none. They just share equally. All right, here's just another little cartoon. Very cute. All right, so just a quick review. Right, covalent bonds, there tends to be very little difference in charges. In a polar covalent bond, you have a slightly different charge, right? Slightly more. And then in an ionic bond, they have a really high difference because one becomes a positive ion and the other becomes a negative ion. So there's a huge difference in electronegativity between them. They become attracted. Alright, so polar versus nonpolar. Here are just some examples of polar bonds. H2O, ethanol, methanol, vinegar, glucose. These are all compounds that form due to polar bonds. And polar bonds usually will take place, covalent bonds in general will take place with nonmetals. They tend to like to share their electrons. Nonpolar, where they share a little bit more equally, would include CO2, O2, N2, H2. Notice that a lot of these are atoms that are just doubled up with one another. Because they're the same atom, they're going to share pretty equally between them. The noble gases, on the rare occasions that you can get them to share an electron, they're not going to give it up, but they might share it. They tend to be nonpolar covalent bonds. Gasoline, oil, turpentine, and other hydrocarbons are all the result of nonpolar covalent bonds. And a covalent bond yells at an ionic bond, "Didn't anyone ever teach you to share?" Alright, so here are some examples of ionic and different types of covalent bonds. And if you think you know these already, feel free to fill them in yourself. Hydrogen, we just already said that it forms a covalent nonpolar bond, shares equally because it's the same atom. Sodium, we already said was ionic. It's a metal, sodium, and chlorine, sodium chlorine, is a nonmetal. So metals and nonmetals tend to form ionic bonds with one another because the metals like to be positive, nonmetals like to become negative. Carbon oxide would be covalent polar. Hydrogen chloride, covalent polar. Ionic, covalent polar, ionic. Again, these two ionic ones that I just showed you, potassium iodine and hydrogen chloride, or beryllium bromide, they have a metal and a non-metal in them. So you can kind of guess that they're going to be ionic when it's metal, non-metal. Two oxygen atoms, that would be covalent nonpolar. Chlorine, covalent nonpolar. Ionic. Lithium and fluorine, a metal and a non-metal. And then calcium, chlorine, metal and a non-metal, ionic. Alright, metallic bonding. Metallic bonding is a little bit different. It's the third type of bonding. And in this, metals lose electrons easily. We've already talked about how metals are good conductors of electrons. So you can kind of think of it as when metal atoms come together, they form this sea of electrons that kind of just flow back and forth between them. And because that sea of electrons is floating, the nucleuses of them kind of end up being more of a positive area, and that forms a kind of bond between them. So you end up with all of these metallic atoms kind of bonded together in this sea of electrons. So solid metals are crystals where free-flowing electrons drift amongst the positively charged metal atoms. The metallic bond is the attraction between the positive metal ion and the sea of electrons around it. So again, because those electrons are flowing all over the place, those nuclei of the metals become positive, and they end up forming this weird attraction between them. Alright, so just a table with some quick characteristics of the three different kinds, the ionic, covalent, and metallic bonds. You've got types of atoms involved. Ionics, like I've said in the past, metal and non-metal, because they're positive and negative ions they attract. Covalents tend to be nonmetals sharing their electrons together, and metallic bonds obviously have to involve metals on metals. What happens to the electrons? They get transferred in ionic bonds from one to the other. They get shared in covalent bonds, and they travel through an electron sea in a metallic bond. Their formation, in ionic bonds, they form crystalline structures. In covalents, they can have a single, a double, or a triple bond, so they can form all sorts of different complex shapes. And in metallic, they can form crystals when they're solid. The state at room temperature, they're all solid, but many are hard and brittle with ionic bonds. Covalent bonds form solids, but many can be liquid or gas. And metallic bonds, they're solid, but they're kind of ductile and malleable, kind of clay-like, flexible, and they have a luster, a shine to them. Alright, the melting points can be very high with ionic and metallic bonds. They tend to be lower with covalent bonds. The conductivity, good conductors of electricity when they're dissolved in water, when you have compounds like sodium chloride, like table salt in water, good conductor of electricity. Covalent bonds, they tend not to be. Those are the nonmetals, not very good conductors of electricity. And the metallics, obviously, very good conductors. Alright, I think I'm going to stop right there because we're about out of time. I hope you've enjoyed learning about bonding. Have a great day.